Alright, in this lecture, I would like to talk about the fast Fourier transform. That is a big subject. And in particularly, we talk about theoretical development for the fast Fourier transform, FFT. But this case, we consider the very general case, which is n, capital N, is equal to 2 raised to any power r. Now, if you remember, in my previous lecture, I consider the case where capital N is equal to 2 raised to the power r, where r specifically equal to 2. So that means we consider the case n equal to 4. Then after that, the next lecture that I already discussed with you, I consider the next case n, capital N is equal to 2 raised to the power r, where r is equal to 3 or r equal to 4, So that is equal to 8 or 16, depending on r equal to 3 or 4. Now, we consider a very general case. Capital N is equal to 2 raised to the power r, where this r could be any integer value. Could be 2, could be 3, could be 4, could be any integer value. So, let's see what happened when we consider the fast Fourier transform corresponding to the very general situation where n equal to 2 to the power r, and r could be any integer value. Well, using the same idea, we say the index k, if you remember, when you have r is equal to 2, when r is equal to 2, that means capital N equal to 4. When r equal to 2, what we have is just these two terms for the value of k. And at that time, you remember, here we say the coefficient before here is 2 raised to the power 0. And here you have the coefficient 2 to the power 1. That's what's happening when n equal to 2, capital N equal to 2. Then, after that, I say, well, what happens if r here is equal to 3? In other words, n is equal to 8 data point. Well, in that case, then, we have to add another term in here, which is 2 to the power 2 times k2. So, for that situation, the value of k should have 3 terms, as I indicated by the red color there in equation 26. So you can see very clearly, right? If you have r equal to 2, then you have 2 terms. If you have r is equal to 3, then you have 3 terms. And therefore, when you have the most general case, r equal to r, then you should have n term. I mean, you should have r term. The reason you have r term is because you go from 0, 1, 2, up to the power r minus 1. So that's why you have r term. So equation 26 that I show you in front of you on this computer screen is just a more general case compared to r equal to 2 or r equal to 3 that I discussed with you earlier. Similarly, equation 27 that you see on the computer screen have the same expression just like equation 26 for the index n. So now, exactly in parallel with the previous development, we say our objective is to calculate the unknown vector c tilde according to this order. And according to the formula, it should be based on the summation of the function f, which is given, that vector f is given because we know the periodic function given to you and at a certain discretized time, multiplied with w raised to a certain power we call capital P. Now, if you have a r equal to 2, then you have 2 summation. If you have r equal to 3, you have 3 summation. Now you have r equal to r in general. That's why you have r summation. You see? Because you have the summation based on the index k0, index k1, k2, k3, blah, 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 up to k r minus 1. And that's why you have r summation. You have r summation. Now, what is the definition of w raised to the power p that you see in equation 28? According to what we learned earlier, w raised to the power p, remember that term p over there actually consists of the first parenthesis, which is exactly, we call it in the early day, a small n, multiply with the second parenthesis. In the early day, we call that guy is small k. Now, if you make use of the definition given in equation 26, that gives you the definition of k, and that's why the formula for k, you can see, will be replaced by that parenthesis right there in equation 29. And similarly, if you look at equation 27, that will give you the formula for the index n. That is exactly what you have here when you replace that index n by equation 27, as I indicated to you in equation 29. So now, equation 29 will give you a formula to compute w raised to the power p. The next thing we'll do, we will try to focus on the power of w as indicated in equation 29. So let's take a look at that particular term. Now, as you can see, what you have, according to equation 29, what you have will be, you take, let's say, the first parenthesis, you multiply with the first number of the second parenthesis. So you take the entire first parenthesis, take the entire first parenthesis, you multiply with the first product of the second parenthesis. That, we just want to do that much, okay? Let's see what happened. So here it is. You take the first parenthesis entirely, and then you multiply that with the first product of the second parenthesis. Together, the right hand side there, we call it w raised to the power p1. So now let us try to figure out what is the answer for w raised to the power p1. And the way to do it is like this. First, you take the first term, the first product of the first parenthesis, you multiply with this term. That will give you the red term that I show you right there for w raised to the power p1. And then after that, what you can do is you take the second term of the first parenthesis, we multiply with the same term over there. That will give you this green term right here. And so on, and so on, and so on, until you take, for example, the last term, multiply with this term, then it will give you this term in here. So all I said to you is you just expand the power of p1. You just expand it, and this is what you got. And then if you look at this equation for the computation of w raised to the power p1, whenever you see the symbol bracket like this, pay attention. Pay attention to those things inside this special bracket right there. If you notice it, all of those terms that I show you inside the square, inside the bracket, it contains something like w raised to the power 2r. W raised to the power 2, and then the whole thing raised to the power r. W raised to the power 2, and the whole thing raised to the power r. Now, how do you calculate that term, which is w raised to the power 2, and then the whole thing raised to the power r? How do you calculate that term? Well, the answer is, according to the definition, we know w, the red term, is defined as everything inside this red parenthesis. In other words, earlier we defined w as e raised to the power minus I 2 pi divided by capital N. Now, don't forget, in this case, capital N, in this case, is equal to 2 raised to the power r. And therefore, this 2 to the power r right there will cancel with this one. You see, these two guys will cancel out. So all you have left is just e raised to the power minus I 2 pi. And when you use the so-called Euler identity, using Euler identity again, that e raised to the power minus I 2 pi is the same thing as cos of 2 pi minus I sine of 2 pi. And again, we know sine of 2 pi is 0, cos of 2 pi is equal to 1, and it means the term that we have, w raised to the power 2 and the whole thing raised to the power r, is turned out to be equal to 1. Turned out to be equal to 1. So that become very very useful for us. So which means every term that you see inside a bracket, let's say this term is equal to 1, this bracket is also equal to 1, this bracket is also equal to 1. And therefore, the formula that you have for WP1 will be simplified to be equal only to this much. And then, after you figure out